Class H is next. Now, maybe a quick comment about math physics and theoretical physics. The traditional math physics course does not do a lot of stuff I'm doing. They specialize in the mathematical methods, but I'm introducing a lot of physics as we go, like the philosophy and fundamental aspects of physics. So my course is sort of a hybrid. It's a traditional, partly math physics methods, most of which will be coming toward the end of the course, so the second half. And the other half is to look at physics in a different way, theoretical physics. So in that sense, this course is very unique, and I don't think you will find that anywhere else, that this particular way of bringing theoretical physics together with the math physics, all right? And today is a good example of that, because today we're going to show how chemistry, properties like temperature, pressure, and we'll be introducing entropy, are related to, say, statistical mechanics, where you have the probability of the particles to be in different states, and the most probable state is the one that's realized. Nature tends to go toward the most probable state, and we'll relate that to entropy. And that's a very, very deep connection to see. And there, we're going to have to be patient with some mathematics, and the math physics part would be like the Stirling formula and how to approximate n factorial if n is large. But we're going to use it within the context of statistical mechanics, or stat mech, and show something very profound by connecting entropy with the number of ways that a system can exist in, say, a given energy level, for example. So that's good stuff, and I hope you find it very interesting, and it connects certain concepts, chemistry, to statistical physics. Chapter H. Statistical mechanics. H1, Combinatorics. And this brings us back to Pascal and the Pascal triangle. Let me phrase this a little differently. Rather than refer to the Pascal triangle, let me show you something by an example. See, we have a family, and there's 5 people in the family. And say that there are 2 tickets to go to the movies. So 2 go to the movies, and 3 stay home. How many ways can we have this situation? Well, we can give the first ticket to 1 of 5 people. And then the second ticket, well, there's 4 people left, so that's 5 times 4. But it doesn't matter which order we give the tickets in, so we need to divide by 2. Or 2 times 1, or 1 times 2, however you want to look at it. And that's the answer. So the answer is going to be 10 ways. It's probably not a bad idea to name the family, give them names, and actually write down to really to master this, like do it the long way, just figure out who the pairs are. But I want to look at this and say I can write this as 5 factorial over 2 factorial and 3 factorial. I can write that like this. And this is very important for our application, because you can think of like 2 energy levels. Going to the movies is an energy level, and staying home is an energy level. And I want to put particles I got 5 particles, and how can I distribute them? And this shows me that if 2 go in one and 3 go in the other, the number of ways to pull this off is this, which is a nice formula, because this is what it's saying is that you take the total number of particles, n factorial, and you do n1 factorial and n2 factorial for the 2 cases where you're going to portion them out, tell them, you know, what they're going to be doing. So that is very, very powerful. And as we apply that to the statistical problem, and we can also call this Stirling's approximation. If we have n particles and they need to go into different slots, n1, n2, n3, how many ways can we do that? Let's let this symbol be the number of ways, omega. Well, you would take n factorial and divide by then the individual occupation numbers, see? So that's the generalization of what we just did. Here we go into the movies, you stay at home, but then maybe, there's another choice. So many are going to go for a ride in the car, and some are going to go to the museum, or some are going to eat dinner. And so you can imagine n being a large number, and this is how it would be the number of ways to put them into, say, certain energy levels. All right. Now, the conditions are going to be that the total number of particles is going to be here, is going to be a constant. That's going to be a constraint. See, what's going to help us here is to think that the situation we're going to realize is the one that has the most ways of fitting in. If there's very few ways for all the molecules in a room to go up in the little corner of the room or something, and that's not going to happen. In other words, we're going to want the one that has the most number of ways. And then the energy level, n1 times, say, the first energy, n2 particles in the second energy level, n3 in the third energy level, and that's the total energy. So this is the total number of particles, capital N, and the total energy. These are going to be constraints. These are going to be constants for the analysis. And then what we're going to do in this chapter is going to do a minimization max-min problem. We want to maximize this. But trying to take derivatives of all these products like this, really, really scary. So if we take the derivative of the logarithm, see if the logarithm is maxed out, then, you know, the omega will be maxed out, say, because basically increasing, you know, larger numbers have, you know, greater logs, and n's going to be really big, you know, really big number. So here we convert the product to now, this is the log of n factorial, and then minus the log of n1 factorial minus the log of n2 factorial minus ... Because remember, when you have the logs, if you have the log of AB, that's simply the log of A plus the log of B. And if you have the log of A over B, like we did earlier in the other class, we had that with volumes and stuff, log A minus log B. So then you have this. This is much friendlier to work with. But another problem is these are still scary. These are still weird. And Stirling has a nice formula to approximate this. Stirling. And we're going to look at a variation of an approximation here, a variant of this approximation, so we can do the problem more easily. So let's look at this, for example. Let's look at one of them. Let's look at n factorial, the log. This would be the log of 1 plus the log of 2 plus dot, 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 the log of n. Because this is, after all, 1 times 2 times 3, dot, 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 times n. And if you have the product, then the log of the product would be the log of each one summed up. You can add them up. So now look at this little observation. Say we have 0 here, say 5, 10, 15, 20, and this is the log of x. So the log of x, now say start out here at 1, so the log of 1 is 0. And we're going to be looking at numbers that are way to the right here. So the log does something like this. Increases, with the number. But if I look at, say, this is like 5 here, and this is the log of 5 up in here. And if I go over 1, see, this is 1, the thickness here is 1. And then I would go, this is the log of 6. And then thickness is 1. So what I'm basically saying is that I can look at this thing as being the log of 1 times 1 plus the log of 2 times 1, because all these widths are going to be 1, plus the log of 3 times 1 up to the log of n times 1. Well, that's the area. Now we're talking the area under the graph, all right? So now we're saying, that's like saying here that we want to go from 1 to n of log of x. We want to just integrate. So what's that going to be? Because that's going to be a nice simplification here to get rid of all these factorials. So here, well, let's review some things. If you take the derivative of the log of x, you get 1 over x. If you take the derivative of x with respect to x, you get 1. Well, what about using the product rule, x and log of x? Well, it'd be the derivative of the first one, which is 1, so you just have log of x. And then plus the first one times the derivative of the second one, which is 1 over. And this is the log of x plus 1. So once when I have this set up, I'm going to subtract here 1. From there, so I can just have the log of x. And here, what I'm really interested in, remember, is go from 1 to n, log of x dx, because that's going to be approximately, right, going to be here, the log of n factorial. In our system here, see, log of 1 plus log of 2 plus log of 3. So this is basically getting you this log of n factorial is this integral of log x dx, from 1 on out. So I'm interested in integrating this, but watch this trick. I can write this as dx log x minus x dx, because the first term will be what I have here, and then when I do the derivative of the minus x, I get the minus 1. So if that's the case, this can get in here, but see, now I can just lift the derivative of them. If I have a derivative and an integrate with respect to dx, I just lift that. So if I lift that like this, 1 to n, that's going to be approximately the log of n factorial. So if I put in n here, I get log of n times log of n minus n. And then at the lower one, log of 1 is 0 minus 1. So this is going to be n log n minus n plus 1. That's going to be our approximation. And since these n's are very, very large, we don't care about that. And therefore we have this nice result. And I'll emphasize that that's approximate. There we go. Much friendlier. So what we're trying to do when we are looking at this log of omega, remember that's your log of the big N, and then minus the log of N1, minus the log of N2, dot, 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 with the constraints that we talked about. So if we look at this and use this approximation, then we're going to simply put down this is n log of n minus n. That's the first one using this approximation. Then the next one, n1 log n1 minus n1. And then the next one, n2 log n2 minus n2, dot, dot, dot. But notice that when you look at, you pull this out, that's a minus n, but then you're going to have here a plus n1, a plus n2, and you're going to add up all the n's, but like all these, that is at capital N. In other words, that's 0. Well, that's good news. That means that the log of this omega, log of the number of ways, is going to be n log big N minus n1 log n1 minus n2 log n2, dot, dot, dot. So that's very nice. And we want to do a maximization of this to find out where these n's would distribute to get the maximum value. Now, H3 is a review of the technique we're going to use, which I reproduced for you in this chapter, but we already did this. The method of undetermined multipliers. We looked at finding the area, maximum area if you have a certain amount of fence, and we did it the regular way, and then we did it with the method of Lagrange undetermined multipliers. So that's what we're going to use, that technique, to do the maximization to maximize the number of ways. So we want to maximize this, but remember the constraint is that the number of particles, they can't change, and the energy, that's going to be fixed. We can't change that. And then what we do is we want to do the maximization of this thing, say, like you take a derivative. So this would be the partial with respect to n1 times dn1 plus the partial with respect to n2 times dn2 plus dot, dot, dot. That equals 0 is going to be your maximizing. And the problem is, though, that you can change the number of particles, the total number of particles. So dn1 plus dn2 plus, that has to be 0. And the energy is constant, so E1 dn1. I'm just doing the differentials here. Epsilon 2 times dn2. That has to be 0. In other words, this is a constant. E's a constant, n's a constant. They're fixed, they're constraints. So therefore, you take a dn, you have the sum of all these little n dn's. That's going to be 0, the overall effect. And then the dE will be 0 also, and this is going in and taking the dn's. The energy levels are fixed. What we would like to do is consider the dn's, the dni's to be independent. But remember the trick, what we do is we introduce two undetermined multipliers. We want d log of omega minus alpha say dn, minus beta dE. And you can think of this as that if you change all these n's, you can't change everything but 2 because there are these 2 constraints which are going to constrain you in some way. But if I do this, pick alpha and beta in a certain way so that I can consider then each of the n's independent. All right, so that's the trick of the Lagrange undetermined multipliers. So here is, we're going to sum up all these and then subtract alpha, the partial with respect to ni, and the partial of e with respect to ni, dni equals 0. So using the laws of partial derivatives and the differentials, we can write, dn and de in a similar fashion using the rules of the partial derivatives. And now I'm going to pick alpha and beta so that I can say these are all independent. I'm going to act as if they're not, but I'm going to force it by picking A and B so it does. I can say that this is equal to 0. See, I couldn't say that otherwise, like up in here, but I can now because I'm going to pick alpha and beta as if these were independent. These can be treated as if now being independent because I pick alpha and beta to force it to work. I'm going to pick those to conspire against the constraints. Okay, so now it's a matter of doing our math. So now what we're going to do is write down in here the partial of the log of omega with respect to ni minus alpha, the partial with respect to say ni, and then minus beta, the partial of e with respect to ni. These are all going to be 0. So the first step will be the work on this one. So what is the log? Well, that's down in here. So we're going to bring this back up here. This is going to be n log n, this one down here. So if we look down at this one, we're going to copy this up in here. And what I would like to do is do one case. In other words, make the I 1. Let's just do one. So it's not in general, but here this is going to be okay. Now all these don't have n1s, so really this is the only relevant piece that's going to be in there. There's going to be an n1 in here, so it's the partial of n with respect to n1. We'll just go ahead and do the chain rule carefully and keep all that. So we'll say the partial of this whole thing with respect to, let's make this with respect to capital N. Let's do that. So the derivative of this with respect to capital N, and then the chain rule, and then the capital N with respect to N1. This next one's very easy because on this one, you're going to be taking the derivative of the first, which is a 1, and that'll just be then the log of n1, and then keep the first one, take the derivative of the second one, you'll get this. So let's work on this thing here. The derivative of the first one is a 1, So this will be then log of n. And then when we do the derivative of the second one, we'll have 1 over n. This is very easy, by the way. This is just 1. Because remember, n is n1 plus n2. And if you take the derivative with respect to n1, you just get a 1. So this is going to be the log of big N plus 1 minus the log of n1 minus 1. So these will cancel, and let's just write down the result from the beginning. This derivative here will be the log of big N minus the log of n1. That's going to be important right there, that one there. Now remember, we need to find these others, but this one's trivial because that's going to be simply a 1. Because when you have this n, it's going to be the sum of all the n's, find wherever the I one is, and then it's going to be dni, dni, it's going to be 1. All right. This one, once again, will have epsilon 1 and 1, but there'll be the epsilon I and I in there, and that's going to pull out the epsilon I. So in other words, when you do here, and go ahead and we'll write this out as just involving the first one. Let's just put the 1 down there. So minus dn, this is the n1, minus the beta de dn1. So this is going to get you a 1, and this will get you an epsilon 1, because that's where the n1 is going to reside. This is going to be n1 epsilon 1 and all the others, but if you take respect to n1, just the epsilon 1 is all you're going to get. So when you do that, put it all together. We want to put this one in for here, and then we have the others, so that would be then the log of n minus the log of n1 minus, then we put in this one, minus alpha minus beta epsilon 1 equals 0. This would be the log of here n over n1, and we could put this on the other side of the equation like this. I want to solve for n1, so what I'm going to do is I'm going to flip this and put a minus sign here, because if I flip this, then basically have a minus sign. Or if you prefer, you can just do this instead. Subtract that one. And then you would have plus for those. And then now this would give you n1 over big N, and then minus. And then this gets you n1 over big N is e to the minus alpha minus, like this. And n1, that's what we're after, is the total number of particles. Now, see, the price I have to pay now is got to find alpha and beta. See, that's the bad news, that you simplified things, but now you got to find alpha and beta. And that takes us to H5. How do we evaluating the undetermined multipliers, alpha and beta? So what do we have? We have the n1 is n e to the minus alpha minus beta e1. But see, now all you have to do is put a little dot on there, and you've done them all, because they're all we just did the n1 case, but really it's the ni case. So let's do one. Let's evaluating alpha. Well, we know that n is n1, the big N. You add up all the little n's, which means if you add up all the little ones, you would have then this with the first energy plus this with the second energy, all the way like that. Now you can write this as an n everywhere, and then we're summing over I e to the minus alpha minus beta epsilon I. Just pull out the n, and then this is summation, you know, I is going to be 1, 2, 3, 4, 5, and get them all. So that means n, I can pull out e to the minus alpha since that's a constant. And I have this. But if I divide by n, I get 1. Now I'd like to solve for e to the minus alpha. So e to the minus alpha would be 1 over this sum. And this is by definition 1 over big Z. And that Z is called the partition function. So let's summarize things. The n I will be equal to n, big N, and forget the alpha one for a second. This is e to the minus beta epsilon I. And then e to the minus alpha is 1 over z. So this is 1 over z. And then we could say that z is the sum e to the minus beta epsilon I. It's the denominator. It's whatever this is. And if you write them out, you know, it's the first energy one plus the second energy plus the third energy, and so on. Okay, now 2, evaluating beta, and Pascal again, because the beta, we're going to use his Pascal's principle here, which we looked at in our first class, that the pressure at the bottom of a fluid volume is rho GH, and if you have water and atmospheric pressure, you can add, you know, P naught on the right side. But that's it. So let's look at that. So let's look at what we did. And here, this is what we did the first class. We looked at this, but let's do a little variation here. This height, let's put the ground down here and let this be the atmosphere, so that this is Z above ground. And this is then the height of this parcel of air, area A, you know, mg, just like we did before. And the pressure here, force per area, we showed that that was rho GH. All right, so that's a formula we derived earlier, which is a very, you know, easy formula, since this is, you know, mg, and the m is the rho times the volume, and the volume is the area times the height. That when you put all this together, in fact, I'm just re-deriving it now. So this is going to be rho AHG over A. That's it. So just replace the F with mg. That's the weight. The m is the density times the volume. The volume is the area times the height, and you get it. So it's we did it before. This is a quick review. So now the thing is, if you look at let's look at Z plus H as some height H off the ground, and we're going to consider measuring up off the ground. So if we measure up off the ground and we fix our attention on this H, say, as a constant, then if you take a dz plus a dh, you get 0. So that means dh is equal to a minus dz. So that means when we look at our pressure formula as a rho gh, and we consider this as a rho g dh, if I measure from the ground, the bottom, I have to use the formula for dp as a minus rho g dz. In other words, the pressure is going to be decreasing as I go up. That's all that's basically saying. We set it up initially as like going underwater where the pressure increases, but now I'm going up the other way. So we're going to have this decrease in pressure as you get up higher and higher in the mountains. So now we're going to look at PV is NKT. You know, it's the ideal gas law, or little n RT, but we're going to use the number of particles. Then the pressure is number of particles KT over V. And let's let little m be the mass of one gas particle. All right, we'll assume all the particles are the same. So then P times a little m is n little m KT over V. And then this is, and you can see now why I'm doing this. This is how I get the density. This is the mass per volume. This is the density. So then I get rho KT. So that trick was needed to get density, because density is mass per volume. So now this means that P is rho KT over M. And then if I do a dP to see how that's going to affect things, constant temperature, we're not going to change temperature, and this is going to be a d rho. So this is how we're going to relate pressure to a little change in the density. But this is, we already have determined, rho g dz with the minus sign from up here. And when we put this together, we then get KT over M d rho is minus rho g dz. That means d rho over rho is going to be equal to mg. It's nice to see mg together and kt together is nice. dz, and there's a minus sign here. So d rho over rho is minus mg over kt. And now we're going to integrate. We're going to integrate this, say from rho naught to rho, 1 over rho. And this is then minus mg kt from 0 to z, some height. This is going to be the log of rho over rho naught. We've seen that trick before. And this is going to be minus mg z over kt. This means rho over rho naught is e to the minus mgz over kt. And rho is rho naught e to the minus mgz over kt. This is the famous result where the density of the atmosphere thins out as you get higher and higher, see? And when I get this, I'm going to use this as insight that this is mgz is my potential energy. And my potential energy here is being divided by KT. But see, if you recall, when you have this Ni, is, say, we go ahead and write down what we had before is, n over the partition function, e to the minus beta epsilon I. This is an energy. So I have an energy here, but I have then a minus sign over kt. This is not a formal derivation, but it's insightful. The Pascal's law is being used here to identify beta with 1 over kt. Because I have energy, I have minus sign, I have beta. Here I have, instead of beta, I have 1 over kt. So that's going to be the assignment, that the second Lagrange undetermined multiplier is the kt, 1 over kt. Okay, and now we go to H6, entropy. If we look at the first law of thermodynamics, change in energy is the heat energy going in minus the work that you do. This is a perfect differential, but these aren't. So we put a little slash. Perfect differential means that you can go from one point to another and your energy here will be the energy there. But see, when you do work, it depends on the path you take. So it's not the kind of function like U that's intrinsic to the system. But this is P dV. They are good variables, pressure and volume. So in other words, by replacing here the dW with PdV, we got good variables that are intrinsic to the system. You could say a gas has a volume V. You can't say a gas has a work, all right? But it does have a volume V, or pressure. Now this one, if I write it like this, du plus PdV, this is still problematic. So let's look at this as deltas. You can always write these as deltas. That's not a problem. And if we use PV is nRT, we know that the energy is 3/2 nRT, which is nice to remember. Then delta U is 3/2 nR delta T. So let's go ahead and do that. Delta Q is, put this in, 3/2 nR delta T plus, and what about this thing here? Well, the pressure is nRT over V, and this is then dV. So in other words, solve for pressure here, nRT over V, and then put that in there to get this. Now I can make this delta Q a good thing by dividing by T. Now watch this trick. If I divide by T, I then get 3/2 nR delta T over T, and then plus nR V and delta V. So in other words, this piece here can be integrated, like this can be integrated. These look nice. And this, now this, if I define this to be equal to some delta S, which I'm going to call the entropy, then when I do integrals here, these are path independent. Like when I integrate, I'm going to have a V1, a V2, a T1, D2. So therefore, this function is one that is a good variable to add to our collection of variables of pressure, volume, temperature, and now I can add entropy. In fact, if we just go ahead and do it, in other words, this ds, this is now good, 3/2 nR 1 over T dt plus nR 1 over v dv. We can now integrate, and we'll get some log here. You have t2 over t1 coming out of this thing, and we'll have here a log of v2 over v1, and everything's looking good. All right, we can then say we have an S1 and an S2 at one point and another. So now we combine and write down du, which was the dq minus the p dv. If you look at this, the delta q is t ds. So that means here, if we go t ds, we don't need to have that slash anymore. And we could then look at this. Very, very powerful. And notice that the partial derivative of the energy with respect to the entropy is equal to the temperature. Now comes the big, big conclusion. If we remember, we had this set up earlier in the class using the method of undetermined multipliers. Now we know that the beta is 1 over kt. So now I'm going to write the beta dE on one side of the equation. Then I'll have a d of the log of the number of ways on that side here, and then lambda dn. All right. Now watch this. If we were to take the partial derivative of E with respect to this crazy thing, the log, we would get here 1 over beta. So you can think of dividing by beta first if you want. If you divide by beta first, then you would have here a 1 over beta. This would be over beta to get you a 1. And this would be over beta, which I don't care about. So I'm taking a partial derivative with respect to this thing. I don't really care about that. But see, this is 1 over beta is this kt. But wait a minute. You said that the partial derivative of the energy, we just used the term u for the other case when we were analyzing this, is t. That means that this, if I put, so this is energy, so the partial derivative of energy, if I put the k with the log here, divide by the k, I get t. Well, that's implying that the entropy is the Boltzmann constant times the log of the number of ways the particles could be arranged. Now, this is a profound discovery. This is incredible, because this is chemistry. This is the macroscopic properties like temperature, pressure, volume, entropy. But this is statistical mechanics. This is stat mechanics. This is the number of ways that the particles are in the different energy states. And I am showing that the entropy is proportional to the number of ways. That means if the number of ways of having something increases, like a messy room, there's more ways to have a messy room, that means the entropy will be higher, all right? And you learned that in chemistry class. But now even more profound, if you had two systems where you had S1 is k times a log of number of ways 1, and S2 is k times a log of number of ways S2. If you were to add the entropies like this, then you would get k, and you would be adding the logs. But this makes perfect sense, because this would be then the log of the product. In other words, if there's a zillion ways to have this first system and a gajillion ways to have the other, then you multiply the zillion gajillion, to find the number of ways for everything. So, because that would make sense. In fact, you could derive this entropy adding by thinking of that. If I have two systems and I put them together, then the number of ways are going to multiply. I would start here. But then I would go to the left and say that means that the logs are added, but the logs are the entropy, so the entropies must add. So that means if you have a system with entropy S1 and S2 and you put them together, you add the entropies. This is worth it. Your struggle with the undetermined multipliers and pushing yourself is worth it to get this payoff. This is an incredible theoretical physics connection to relate chemistry to statistical mechanics. Just awesome. So we will conclude here with a nice way of looking at the laws of thermodynamics. The first one is no free lunches. And the second one is you can't break even because the entropy will always increase. When you put systems together and have a number of ways they're going to increase, you're going to increase and increase. First law, here it is. The energy change of a system, it's the heat going in minus the work done. And you can't get something for free. Conservation of energy. And then the law of entropy for the second law is that the entropy will always the universe going to increase. And you can think of the entropy as the Boltzmann constant times the log of the number of ways that particles can exist in their energy levels. And to relate this to engineering, when you have engineering systems, like you have energy in an engine being shared with some work done, and then you waste some energy. And we calculate the efficiency of an engine, the last class. And the refrigerator, by the way, is the reverse. You would put in work energy to remove heat from a cold source to outside, and then you would have a cooler environment. And then this is your efficiency, which we talked about for the engine, the work done divided by the heat that's going in. And that's going to be less than 1. In fact, the second law of dynamics specifically says that you can't break even. In other words, you cannot have a perpetual motion machine, because if you could put the energy back in, it would go forever. But if you can't break even, you have to waste some energy. You always have to waste some energy. So these are the 2 rules and good principles in life. No free lunches. When you get that phone call that says you're going to want to give you something for free, you know they're up to something. Don't fall for it. And then here, whenever you lose some money or something gets lost, just think that's the second law of thermodynamics. That's going to happen. You're not going to break even. So kind of helps you accept things in life a little better and operate in life a little better by remembering these 2 rules. No free lunches, and you can't break even.